Hello class. This is going to be a series of videos where we review what I would call introductory information about building structures that you've already covered in your education to date. But hopefully I'm going to put it in a different context and a very applied one for your studio work. So the first thing to remind yourself of is that we should be reading Ching's Building Construction Illustrated textbook. And really, there's a very good series of chapters on this information. I'm highlighting here sections 210 to 226, as well as 236 for joints and connections. Now, we're going to do a bit of an introduction here about introductory components, stresses, and forces. So when we're building buildings that we have a structure and structural function to, we should understand that there's certain types of structural forces or mechanical forces. Those are tension and compression, bending, torsion, and shear. And that covers most of what we have to worry about. Now, when we're designing, we're responding to these particular forces. And we do that with a requirement of having sufficient strength to resist and transfer the force, but also, and it's easy to forget this, sufficient stiffness. Because in most building applications, if something is too flexible, it can't fulfill its purpose. So the strength and stiffness depends on a number of factors. It is a big mistake to think that the primary concern is material. So people think, well, steel is strong, concrete is weaker, and wood is weaker yet. But that's actually very unimportant. Those differences in material are, of course, critical to designing the actual structural stiff system. But we do this by modifying the geometry to respond not just to the loads, but also to the material that we're using. And we're using these materials for a number of reasons. The geometry, I mean the cross-section. If I cut an element, what is the cross-sectional shape and area? And in terms of the element, which I mean such as a beam or a column or a truss cord, that also has a geometry that doesn't have to be the same from end to end. Then we put these materials that we've chosen, both the cross-sectional and along the length geometry, in a structural system. And now we have something that we can analyze strength and stiffness for. Now, the last thing that we can't really ignore is that a load is not just a load. There is also the kind of load. Is it a load that acts on the system, materials, elements for 1 second, 1 minute, 1 hour, 1 month, 1 year, 1 century? Because many materials will respond differently if you have a short-term load than a long-term load. So materials such as wood, bamboo, etc., natural materials, tend to be much stronger under short-term impact loads than under long-term, year-long, century-long loads. Materials like steel generally are pretty similar over longer time periods, although they may be a bit stronger when it comes to short-term loads. And other materials actually are more sensitive to impact loads than they are to long-term loads, materials like glass. So when I'm describing materials, if I go through that list now, the most important metrics for materials is the modulus of elasticity, which assesses its stiffness. Then we have, for strength, yield stress, the stress it takes to pull a material apart, crushing stress, the amount of stress it takes to smush it together, and shear strength or shear stress. So, of course, knowing these material properties allows us to choose specific areas, specific shapes of our section, and we're going to get into that. But first, a quick review about what does it mean by stress. In the lay world, people will often say, I'm under a lot of stress or I'm under a lot of strain, as if they're the same thing. Whereas when it comes to structural engineering, stresses are a very particular thing. It's force per unit area. And the forces that are imposed on different structural elements by different loads create different stresses depending on the geometry. So the most obvious and simple consideration is to either extend or squeeze a column or a bar of metal. And this, knowing the area, we divide it by the force divided by the area gives us the stress. And we're either stretching it, following the Pli rule, load P times length of the element L, all divided by the modulus of elasticity times the area. That tells us how much it will stretch. Tension stress, of course, just the force P divided by the area A. Compression strength, the same way. When it comes to bending loads, well, of course, the stress is not simply the area, the force divided by the area. The forces are now have differential stresses acting across them. From the neutral axis of bending up to the extreme fiber, there is a linear increase in stress. And this is something that we are supposed to study in some detail in structural mechanics. And so I'm assuming that you're pretty comfortable with this. Now, what we do always have to keep in mind is that the maximum stresses are at the extreme fiber. But what I mean by extreme fiber is the fiber of the material that's at the greatest distance from the neutral axis. And that is very commonly because it's a linear elastic assumption. We create a triangular stress distribution, as you can see on the right side of this chart. And this allows us to predict both the resisting capacity of a bending element, but also the stresses that will result from bending imposed on a bending element. Another form, of course, that we have to deal with of forces is shear forces. These are the forces which are the result of a translational intention across the section. And that causes a shear force, and the stress is simply the area on which that shear force acts, and the force divided by that area gives us shear stress. We often, if you'll recall solid mechanics, use tau, the symbol, to define or describe that. Now, for every vertical, let's say perpendicular to the neutral axis shear force, or creating a shear stress, there must be a balancing shear stress along the length of the element. This is something we often don't give enough consideration to, but we use shear flow to describe how the shear is accumulated over the height of the element. And this is a great image here from the Efficient Engineer, a website I highly recommend, where they have some good visualizations of how stress is transferred across different types of elements. Now, we talked about bending stress, but there's also torsion stress, which is rotation. Torsion is a rotation perpendicular to the long axis. And this is sort of like a twisting, not a bending stress. And much like the bending stress, we create a torsional shear, which is perpendicular to the centroid or the neutral axis of rotation. Torsion stresses are really important for many machine components, such as machines like electric motors, internal combustion engines, etc., because we use shafts to transmit torsional or torque energy and power. With structural design, we often have to deal with some torsion, but we try and minimize torsion by our selection of geometry. But more to that in a little later. So again, showing an example of a drive shaft, for example, that runs a piece of machinery. We impose a torque. It causes torsion, and that causes torsion stresses. And this will, as a deformation, cause a twisting, as shown here in this image from the Efficient Engineer website. Now, when it comes to building structural design, as I mentioned in the introduction, we have a selection of materials, shapes, and systems to resist the mechanical loads and forces without failure. So our job in our design is to make sure that those selections are proper so that it doesn't fail. Well, that means we now need to know, why would it fail? What causes failure? Well, there are actually a number of failure modes which are implicit in a lot of the forces that we've already talked about. So we worry about yielding or fracture of a material when it is being extended or put into tension, or the tension side of the bending. We worry about crushing when an element or material is being compressed, and that means it's on the compression side of a bending element. These yielding and crushing modes have different material properties that would be used to say, don't exceed a certain stress to avoid yielding or fracture. Try and stay below a certain stress so that we do not get crushing in compression or bending. Then we have failure modes like shearing, and shearing caused by shear stress. And there again, we have loads. Many times, for example, the shear stress that's allowed is assumed to be 2/3 of the yield stress for an isotropic material, for example, like steel. Buckling is an actual overall mode. It's not a material mode, and so we'll talk about that next slide. And then we have an even more complex mode called durability, where we have to consider many environmental factors and time spans to assess whether or not the material and or element and or system fail because of the environment they're put into. Buckling is actually not a material property. It's an element failure. So as you move from just the material cross-section, where we worry about shear, tension, and compression, we start moving up to the element level. And the element level is susceptible to buckling failure. And so we need to assess when buckling may occur. It can occur under tension. It cannot. But any component of a cross-section that is under compression may buckle. And that includes whether it's in torsion, bending and torsion, flexural torsion, or just straight compression, which we usually study early in your career using the Euler buckling equation. The buckling strength of an element depends, whether it's a beam or a strut or a tie, depends on the geometry, and it depends on the elastic modulus of the material that's used. So the structural elements that we make up our buildings and structural systems out of are largely separable into struts, ties, flexural elements or beams, and compression elements or columns. So the strut is a material that resists compression. A tie is a component that resists tension. And a beam is a component that resists bending. And a column, mostly vertical compression, although some bending, which gives rise to sometimes the beam column, beam-column element, which is a column that sees enough bending to be worth designing for. So those are the pieces that we tend to make our structural systems out of. And when we're dealing with a beam or a column, particularly made out of a non-rectangular shape, we'll label the parts of the cross-section things like flange and web. These are very common in wood and steel and concrete, I-beams, H-beams, etc. For simple beams, you should be confident to use an equation to assess what is the maximum stress or what is the total allowable moment resistance depending on the shape and the size and the moment, etc. So there are pretty straightforward equations for simple shapes that I'm just representing here using the triangular stress distribution, which would be assumed for uncracked concrete, wood, steel, aluminum, glass, etc. Another kind of element that we use is built up of actually multiple struts and ties and bending elements. So we're going to be talking about trusses a fair bit, and the truss has its own language. Those diagonal elements, they actually connect a top chord to a bottom chord. We don't talk about a top flange and a bottom flange when it comes to trusses. We talk about chords. And the web is still called the web, although it's not a solid sheet of material. It's just an element that connects. And those elements are not called struts and ties, partly because although they may be a strut or a tie in some trusses some of the time, they often are both struts and ties, depending on the load condition that the truss is experiencing. The very common steel joist that we see, or the open web steel joist, is a parallel chord truss where we see it's all made of steel, and these are like everywhere in longer span roofs and in a lot of medium span floors in commercial construction. Now, one of the reasons we use trusses rather than I-beams, and we use I-beams rather than solid square beams, is for something called efficiency. And I think it's important to talk about efficiency here in that it's a very loaded term, and in most cases it is actually not a desirable trait or not a high priority trait, and it's not even a well-defined trait. So for example, efficiency in a structure might refer to the lowest cost system. That's a very common concern in buildings. When it comes to things like airplanes, they're very concerned about the finished weight of the structure. So strength to weight ratios and efficiency of weight is a very important factor. For buildings, strength to weight is just not that important. The cost is more important. The amount of labor saved is actually an important driver, which explains many structural systems used today, even though they may use more materials than a other system. So very carefully about defining the term structural efficiency. Is it the lowest cost, lowest labor, lowest weight, lowest material system, fastest to an system, etc.? These are all different ways of defining efficiency. Now, that said, there is an interest in almost all cases to reduce the amount of materials and be a lighter weight system, all else being equal. Now, nothing is ever else equal, but just keep that in mind. So one of the reasons that efficiency for structures has changed over the centuries is that we have access to many more interesting materials than we had 300 years ago. If you were building a building in the Philippines 300 years ago, you had a limited access to materials and labor. If you were building in Scotland 300 years ago, you had a limited access to materials and labor. Today, there are many more materials and systems and specialist labor available all across the globe, particularly for large projects. That meant that over those, let's say, last 300 years, we've started to see a whole bunch of new materials and new systems developed that were possible and that saved on mostly expensive materials and or expensive labor. And in the early days, in say 1800, labor and safety were not very important. And so saving materials were. And then over time, labor began to be the more expensive component and materials costs became less important. And we saw direct changes to the structural design of buildings because of those shifts. And that shift of saving labor and making construction faster is a trend that has continued to this day. However, we're starting to see headwinds as people begin to worry about sustainability. Material efficiency and sustainability are directly connected. If we can reduce the amount of materials and if we can switch to materials that have lower environmental impacts, are more widely available and renewable, now we're starting to put more value on those materials. And that is pushing us towards structural systems that have higher degrees of material efficiency. So at the very simplest level, we have solid joists and slabs as being not the most material efficient, but inexpensive to build, doesn't require as much design time. And then as we move through, we start to see things like I-beams with holes in them. We don't use solid plates of steel. We use corrugated plates of steel. We don't use just chunks of, say, steel. We would use stress skin panels. I see that it's spelt wrong there. And then eventually we really open things up to be trusses and three-dimensional space frames. And one of the things that we see is that we are removing material where we don't need it. That's sort of a key to structural efficiency. And one of the most effective ways of doing this is also to have elements, structural elements that change along their lengths. And we'll see that in pre-engineered structures. Another thing is to focus more on strength and not on stiffness. This is a problem because, of course, stiffness is needed for a lot of usability reasons. It's worth looking at basic calculations to understand how some ideal structural systems come about. So it should be pretty obvious to most of you that a rectangular element of any material, say we'll call H high and B wide, will have its neutral axis in the middle, and we'll have a moment resistance equal to something like BH squared over 6 times the yield stress. Now, maybe you don't know where BH squared come from. It's basically, that's the section modulus. And this is also simply the moment of inertia divided by the depth to the neutral axis, which in this case, the moment of inertia is 12. You divide that by h over 2 and you get the section modulus. This is fundamental entry-level stuff when you're dealing with structural analysis. So looking at this, you should be able to recognize that for the same material use, you can get a much stronger beam. And the stronger beam would look something like, this, say. And for the same area, meaning B over H, B times H is the area, our moment now would be significantly larger because our H, our new H, is significantly greater. And since the moment varies as the square of H, the moment resistance, you can see that for the same material, you get a way stronger system. So then the question might be, well, why don't I just make it really thin and really tall? Well, the reason is that when we have a beam of that format, we run the risk of it buckling sideways. This is called lateral distortion or lateral buckling. And it's actually very undesirable because suddenly it'll kick out. Now, one of the things we can do to make this work better is that we can shape the beam in a way that you're probably quite familiar with. And that would be shaping it, well, let's put a lot of the area far from the neutral axis and remove all this extra material right here, right? We're getting rid of all that material. And now we're actually concentrating the compressive stresses on the top here and the tensile stresses here at the bottom. And so you get a larger moment arm, and it has the advantage that it doesn't buckle sideways. Now, you still, if you're doing detailed design, you need to worry about it buckling sideways because it can still buckle sideways. And it is actually, this is one of the limits to the design of I-beams is, yes, we keep making them deeper and putting lots of steel up here and down here, very thin webs, but the challenge is that they can still buckle laterally. So you got to check that. And then finally, the next step in efficiency would be to say, I wouldn't say finally, but let's say the next step in efficiency is to have, well, put your steel here or your wood at the top and the bottom or your concrete, and then just connect them together with diagonal elements. And those diagonal elements are not just removing the material I've shown here on the sides, they're also cutting holes out. And intermediate to these are things called castellated beams, which if you might see them sometimes, will have holes or triangles cut into them. And they cut into the webs. So you can see how it's a step from the beam to the perforated beam to the truss. The advantage that both these perforated webs have is that you can run ductwork through this. You can run pipes and wires easily through this. Beams that look like this have some serious limitations about, well, you're going to probably put your ducts in between them or underneath them, not go through them. So just to recap, when it comes to the terms of material efficiency, strength is often not the limiting requirement. It is actually other factors, particularly stiffness or excessive deflection, and other issues like fire resistance, aesthetics, ease of assembly, and so on, which actually govern the final choice of a material shape and often even structural systems. And one example of the importance of things like deflection is that a tensile structure, such as a tent, is without a doubt the least material that one could use if you measure the material based on, say, kilograms per square meter. But try walking on a floor made of tent material. It becomes completely impractical. Similarly, it may be desirable to structurally use corrugated sheet metal as a flooring system, but the corrugations mean it's very difficult, unsafe, impractical to walk on. And in the case of a fire, the fire resistance rating would be measured in a minute or two. And therefore, we would often choose something different. So summary here is that, the shape of the structural element, the system that is chosen to put the elements together are just as important as the material. In fact, often they're more important. And an understanding of the general relationships of strength and stiffness, such as how the deflection varies, how the strength varies with span, with loads, etc., can be really effective at guiding structural system choices, structural material choices, and guide you to how to change assemblies, materials, and elements for your project, for your purpose as much as possible.